First of all, it's great to be here. Thanks for having me as part of your panel, and look forward to it. So I'm Rajesh Rao. I'm a professor in computer science and engineering. I have research interests in several different areas. So I work in the areas of computational neuroscience, which is using computer science techniques to understand the brain, and also work in brain-computer interfaces, which is designing devices that can interact directly with the brain, and then finally also using ideas from neuroscience to inform the design of AI, artificial intelligence techniques and algorithms. I'm also the co-director of the Center for Neurotechnology, which is a center that tries to build these devices that can help patients with neurological conditions. I teach classes. I'm a professor, so I teach classes in computer science and in the intersection of computer science and neuroscience, neural engineering classes, for example, that I'm teaching right now, a capstone course in neural engineering, project-based course. And then also other things I do during my daily work is meet with students, my graduate students and undergraduate students doing research in these areas. We have lab meetings every week, so meeting with everybody to get updates from everybody. And then finally, there's also administrative things that I do as a faculty member. So we have faculty meetings in the Department of Computer Science, in the Allen School of Computer Science and Engineering. And then we have faculty candidate recruiting that we do. And I'm also part of university level initiatives, like there's a neuroscience initiative that I'm part of the team that is figuring things out there. So that basically covers, I think, everything I do as part of my daily work. So as I mentioned, I work in these areas called computational neuroscience and also neural engineering. So as an example, in computational neuroscience, we're interested in understanding how the brain works, and we want to do that using ideas from computation. So we're specifically at this point looking at this idea that all our brains build models of the world. So we're able to predict the consequences of our actions. So for example, even a baby can predict that if I take something like this cell phone and I drop it, it's going to fall, right? So you learn the effects of gravity. If you push something off a table, it'll fall, or if you bang something, it'll make a noise. So these are all things that we learn as part of growing up from the time we're babies. We're constantly learning models of the world. We learn models of people, right? How people react to language. When you say something to somebody, they react in a particular way. So the key there is prediction, right? So we're developing a theory called predictive coding. Specifically, we call it active predictive coding because we're always taking actions and then learning the consequences of actions. And so we're looking at how can that explain, different aspects of neuroscience. So different kinds of data that we're getting from humans, from other animal models and things like that. And so we're trying to understand how the brain works through these kinds of predictive models. And then we can implement these and test these out on the computer by running simulations, getting data from videos or speech and things like that. And we can test our models as well on the computer. So that's an example of how we can start to understand the brain by using ideas from AI and from computer science. We hear about this all the time, the kind of biased responses you get from AI that's been trained on a particular data set. And typically it's the sort of the dominant voice that is typically trained in these AI, and many of the minority voices don't get heard. So I think that's something that's a huge problem. And we're developing some ideas there. So we're inspired again by how humans do it. So if you think about how human babies, for example, learn what is a moral thing to do, how do they learn to help people, how do they learn to be cooperative. We learn through interactions with other humans. And we also do it within our families, and we do it within our communities. And so what we're developing is this idea of culturally attuned AIs. So the AI is going to grow up, quote unquote, in the community that it's been deployed in. And so we have some proof of concept experiments that we've done where we've had people of different communities interact virtually on the web, playing a game where they have the opportunity to help another player, which turned out to be like an AI player, wasn't a real player. But for them, they had the opportunity to help them, score some points, for example. And we observed that certain communities tend to be more helpful. They help other people more than others. And so we've trained an AI to mimic those kinds of behaviors. And so we're calling that a morally tuned or culturally tuned AI, or a culturally tuned moral machine. And we believe that's the way to eventually do it is, you want to have AI that can learn from the human community that it's been deployed in. And it has to keep learning all the time because societal norms change and they're different for different communities. And so we cannot have a one-size-fits-all kind of AI. And there's different rules and regulations in different countries and different communities and different cultures. And so we are starting to develop those kinds of ideas, and we're using ideas from AI, like inverse reinforcement learning is what we're using to learn the value systems of people that the AI is interacting with. So I think something like that is required as we scale up, robotics and robots are deployed in different communities, is being attuned to the values of that community. Yeah, I think that's a great, very grand kind of question in terms of why are we interested in our past? Why is history important? I mean, obviously, the answer you hear typically is we need to know our history so we don't repeat mistakes that we made in the past, which I think is an important consideration. And more broadly, I think we need to know where we came from. And so we need to know who our ancestors were and, what did they do? And so for communities, some of these civilizations like the Indus civilization, they flourished about 4,500 years ago. We know very little. And so for many of these ancient civilizations, we know things from archaeology, but we're not able to read what their language really is telling us. In my work on the Indus script, we were applying, again, techniques from computer science. We were learning to interpret those particular sequences of symbols in terms of, are there any predictable patterns, right? Are there any irregularities? And one of the big questions that was at that time really prominent question was, are those symbols even representing language, or are they just random symbols that they were using for religious purposes? And so we basically applied some techniques from computer science, computed the entropy, which is how much randomness there is in these strings of symbols, and we showed they're not really random at all. They have some kind of pattern to them, which seems to be more similar to the kind of patterns you see in modern day or in ancient languages that encode spoken word and actual language. And so we provided the first clue without actually understanding what the words are saying there, but just a clue from just analyzing the patterns that at least pattern-wise, they seem to be similar to how we have scripts to encode language, different kinds of language. So I think that kind of a result helps us to better understand, okay, what were they using symbols for? Are they similar to how we use symbols nowadays in our civilization? And I think it helps us to better understand our past, right, and where we came from. So I think just in terms of human beings, I think that's a really important thing for us to do, is to understand the past, so then we can learn how to live in the present and how to shape and how to build our future, right? I think it's important to know our past to build our future. Like a lot of kids, I grew up watching Star Trek and Star Wars and a lot of science fiction, reading a lot of science fiction, novels and things like that. And I think that definitely sparked my interest in AI and also, neuroscience, right? In terms of how the brain works and why don't we have devices that behave like the human brain and so on, right? And that's essentially where I am today, is trying to understand the brain on the one side, because I want to understand us as humans and how we behave and so on, and why we behave the way we do. But also at the same time, it gives us insights into building, artificially intelligent agents, hopefully for the good, right? I mean, we want to make sure that we put the safeguards there for that as well. I think there's already been lots of work in that area. Broadly speaking, you can use it for different kinds of analysis of images, like MRI images or CAT scans, things like that. People have done a lot of that, right? Image analysis. And the idea there is you can really have high throughput kind of, in places where you may not have the kind of machines to do the analysis, or you may not have doctors or clinicians to do the analysis. Perhaps the machines can help. And in the future, I think as we go from just analysis to help doctors to maybe even doing diagnosis, we're not there yet, but if these AI can be trained to essentially do the kinds of things that doctors do, right? And even going beyond that, if you train them on the expertise of multiple doctors, then you can imagine that the performance of those AI engines, those AI doctors may even be better than any one single doctor, right? Right now, I think that's not happening, but in the future, there's always that possibility that may happen. And unfortunately, I mean, we're not going to have that human touch, right? And a lot of us would like to have a human being to interact with. But who knows, maybe in future generations, they would not, they would place a premium on accuracy as opposed to having that, just one-on-one interaction. So we don't know yet how that's going to proceed. But I see that as that automation is going to happen more and more because the accuracies are going to go more and more higher. And these AI, machines or doctors are not going to have, these AI doctors are not going to have things like fatigue. They're not going to be sleep deprived, for example, right? Which may lead to misdiagnosis, or, AI robots are not going to get sleepy when they're doing surgery and forget like a forceps inside your intestines. That's happened with humans before because we're so, we get tired, right? Yeah, so this goes back to that project that I was mentioning earlier, which is based on, predictive coding, and more recently something we call active predictive coding. And so this has been a theory that came out of neuroscience. So we were observing how in the brain there's, a particular architecture in this area called the neocortex or the cerebral cortex. So the idea there is that, traditionally there's people have thought of the way that we process information, we as humans and even animals, is that you perceive something. So you see an image of something. There is a part of the brain called the visual cortex that processes that information and perceives, you eventually perceive it to be, okay, yeah, this is actually a cup, right? And then there is a part of your brain that makes a decision, maybe in the frontal part of the brain, the frontal cortex makes a decision to grab the cup. And then eventually you get to the point where that frontal part of your brain will send commands over to the motor cortex, which then sends commands to the spinal cord, and then you eventually grab the cup, right? So it used to be this very, what is called a feed forward, or kind of, a step-by-step kind of process that was all parceled out in different areas of the brain. But that particular kind of model does not acknowledge the fact that every area of the brain that's doing some processing also sends feedback or connections back to the original area. So the visual cortex gets information from the motor cortex, and it seems like they're talking to each other in a sort of closed loop, right? Which is visual cortex is saying, here's what I see. Motor cortex is saying, okay, use this information. I'm going to execute this action. Now change your expectation of what's going to happen next, right? And it goes back to prediction. And so we built this architecture that essentially does predictions all the time. And then whenever there's a deviation, a surprise, right, or a novel thing happens, something that doesn't meet your expectations, there is a prediction error, like an error in your expectation. And that's a very, very useful signal because you can use it to do two things. One, you can use it to direct your attention that something novel is happening over here. Hey, the door knocked, right? So there's somebody knocking on my door. Or you can also use it not just to direct attention, but also to learn something new. So now I can use that error signal to then change my brain connections, and that's called plasticity or learning, right? I can learn a new person now, right? The same prediction error signal. So we're now building these systems that learn models of the world using the prediction error signal, right? As well as use it to direct attention to different kinds of parts of the scene and so on. And I think it's a very universal kind of architecture. You can apply it to, vision, you can apply it to speech, language. You can apply it to solve problems like planning a route from here to, your house, things like that. Colleges. So for example, we partnered with HBCUs like Morehouse and Spelman, had their students visit us for our summer REU programs. And then we've had, programs within the center and now even separately funded from the center for neurodiverse learners. So students who are neurodivergent, they have, different ways of learning and studying and so on. And then this is a program where we have workshops where we bring in these neurodiverse students and have them learn about neuroscience. So we call that NNL, or Neuroscience for Neurodiverse Learners. And it's still ongoing. It's another year of funding in that. And so we're able to impact multiple communities with these kinds of programs. And we go from high school, or middle school, high school, all the way to, grad school, right? And in my lab also, I make it a point to try to bring as much diversity as possible by having, especially in computer science, I think we have a lack of, especially, female students, right? So I think having more engineers who are female and having more engineers from other communities, right, is really important in computer science and as well as engineering. And that's something that I also, I'm quite committed to doing. So I think overall, I would say that, we've had some successes. I think we can do better, right? So, but we're trying, our best to increase the diversity, both in computer science and engineering, as well as broadly speaking, neurotechnology and neural engineering. from a neuroscience perspective, I can bring in my knowledge of neuroscience to bear and say, okay, there's a reason why we have certain emotions. There's actually a computational reason for it. And, should AI have emotions, right? There's different kinds of debates about that. So I feel like, knowing about the brain and neuroscience gives a whole new perspective on being human, right? Not to say that's the perspective to have. I mean, I'm biased because I've been studying the brain for a while, and I feel like that's the biggest, challenge that humanity faces right now in terms of a scientific question, and also beyond science, right? Being able to understand why do humans behave in a particular way that they do, right? Both good and bad. I do things other than science, right? So, I like being out in nature. I mean, that's something that I do, like hiking is great. I love that. I engage in activities like racquetball and badminton and table tennis and things like that. In terms of art, I have a lot of passion for Indian art. I mean, I come from an Indian heritage, so especially classical Indian art. So I guess I guess some people think that could be my second profession is Indian art history, because that's my bedtime reading, right? So basically every night that's what I read is Indian art history, right? So I know a lot about Mughal paintings. I know a lot about like Rajput paintings. I know a lot about Pahari paintings. These are all like different schools of paintings. I know about company paintings. These are like when British were in India, they had their own set of paintings that they got made from Indian artists. And I have a few at home as well. So I like do my own matting and I frame paintings. I have them, around the house. So I think that's my other passion is, Indian art history, right? So that's something that I would love to do at some point is combine my two passions and sort of bring some of my computer science and AI skills to bear on Indian art, right? So who knows, something in the future.